All right, so we've got these geography textbooks ready for a deep dive. We're talking the whole shebang, from the Big Bang to the Earth as we know it.
It's a wild ride, billions of years in the making. We'll be tracing that journey using these four textbooks, from the universe's beginning all the way to how our planet actually formed.
Let's do it. Big Bang, right? That's where it all starts.
Exactly. Imagine everything squeezed into a space tinier than you can even imagine, then boom, the Big Bang, 13.8 billion years ago.
13.8 billion. Okay, that's a lot to wrap my head around.
And get this, the universe didn't just sit there. It started expanding, and it's still going.
So everything, our planet, the stars, even those far-off galaxies, it all came from that one event.
Exactly. Think of it like a balloon. You draw dots on it, each one a galaxy. As you blow it up, the dots spread out. That's the universe always inflating.
That actually makes sense. So we've got this expanding universe. How do we get from there to, well, us? Stars, planets, life.
Now we're talking. As the universe expanded, it also cooled down. Big clouds of gas and dust, we call them nebulae, they started clumping together because of gravity. That's how stars were born.
So stars are like giant balls of gas that got squished together.
Pretty much. But here's the wild part. Those early stars weren't just shining. They were busy making the ingredients for everything around us.
Wait, like the stuff in this microphone or my chair? They were made inside stars.
You got it. Deep inside those stars, under crazy heat and pressure, lighter elements like hydrogen and helium fused together. That's how we got heavier elements like carbon, oxygen, even iron.
No way, that's incredible.
And eventually these stars went out with bang supernovas. They scattered these newly made elements everywhere. And that scattered stuff, that's what formed new stars, planets, even us.
So I'm really made of star stuff, mind blown. But seriously, how do we go from stardust to planet Earth?
About 4.6 billion years ago, in our own Milky Way, a cloud of that stardust started coming together. Gravity did its thing, pulled everything in tighter and tighter, spun it faster and faster, and
Wait, are you saying Earth formed from leftovers like cosmic crumbs after the stars were made?
you got it. And that spinning cloud, under all that pressure, it ignited. That's our sun. And around that newborn sun was a disk of leftover stuff. That's where Earth and the other planets came from.
So the sun's shining, Earth's forming, but you said it wasn't exactly paradise at first, right?
Not even close. Picture this. A molten volcanic world, constantly getting slammed by asteroids and comets, no air to breathe, just a thin atmosphere of hydrogen and helium. The surface, all magma, totally different from the Earth we see today.
Talk about a rough start. So how did we go from molten mess to, well, a place where we can actually live? This is where those layers come in, right? So last time we left Earth as this molten, fiery ball, not exactly a place you'd want to visit. How do we go from that to a planet with oceans, continents, life? Those layers, they hold the secrets, right?
Absolutely. Those layers are the key to how Earth went from a ball of fire to the planet we know today.
But how do we even know what's down there? We can't exactly dig to the center of the Earth and take a peek. Or can we?
We can try. Scientists have drilled crazy deep into the Earth. Ever heard of the Kola super deep borehole? It goes down over 12 kilometers.
12 kilometers, that's pretty deep.
It's an amazing feat, but it's just a scratch on the surface when you think about how big the Earth really is. We need other ways to figure out what's inside.
So if we can't just dig down to the core, how do we do it?
That's where it gets really cool.
Yeah.
Scientists are like detectives. They use direct and indirect clues to put the pieces together.
Clues. Like what's direct evidence when you're talking about something as massive as the inside of our planet?
Well, there are projects like the Deep Ocean Drilling Project. They drill into the ocean floor and bring up samples, actual pieces of the Earth's crust.
Okay, so actual rocks from deep down. That makes sense. But what about even deeper, the parts we can't reach with drills?
That's where the indirect clues come in. Believe it or not, earthquakes are a big help.
Earthquakes. I guess they do shake things up a bit, literally. But how do they help us understand the Earth?
It's those vibrations. Earthquakes send out waves, P waves, and S waves. Imagine them like sound waves traveling through the Earth.
I'm with you so far. What's special about these P waves and S waves?
They act differently depending on what they're traveling through. P waves, they're like the fast lane, going through anything, solids, liquids, gases. But S waves, they're pickier. They can only go through solid stuff.
So by watching how these waves move or don't move, scientists can create a map of what's down there.
That's the idea. It's like giving the Earth a giant ultrasound. Just like doctors use ultrasound to see inside our bodies, these earthquake waves help us see inside the Earth. We learned about the different layers, what they're made of, how dense they are.
That's incredible. So what have we learned? What's the inside scoop?
Well, one big clue came from something called shadow zones. Scientists noticed that some areas on the opposite side of the Earth from an earthquake wouldn't get any S waves at all.
Shadow zones. Sounds kind of creepy. Why does that happen?
It's the Earth's core. Remember, S waves can only travel through solids. Those shadow zones told us there's a liquid layer deep inside the Earth that the S waves couldn't get through. That's how we know about the Earth's outer core. It's a massive layer of liquid iron and nickel.
Hold on. So under our feet, there's this giant ball of molten metal just sloshing around. How is it even liquid? Shouldn't it have cooled down by now?
Great question. The Earth's core is hot because of radioactive decay deep inside the Earth, plus leftover heat from when the planet formed. It's like a giant natural nuclear reactor. And this liquid outer core, it's always spinning, which creates electric currents, and those currents.
Create a magnetic field. That's what protects us, right?
Exactly. That magnetic field shields us from harmful stuff from the sun and space. Without it, life as we know it wouldn't exist.
Wow, I never realized how important that liquid outer core is. It's like Earth's force field,
Right.
all thanks to a giant ball of molten metal. But wait, you said outer core, which means
You're one step ahead. There's also an inner core. And here's the wild part. It's even hotter than the outer core, but it's actually solid.
hotter but solid. How does that work?
Pressure. The pressure at the Earth's center is unimaginable. It's so intense. It forces those iron and nickel atoms so close together that they become solid, even though it's incredibly hot. Imagine squeezing something so hard it goes from liquid to solid. That's the inner core.
My mind is officially blown. Molten Earth, solid core, a liquid layer creating a magnetic field, and all of this is under our feet. This is incredible. Okay, I'm still trying to wrap my head around a solid ball of iron bigger than the moon just hanging out at the center of the Earth. But we're not done, are we? Layers are one thing, but what about the continents? Why aren't they content just staying put?
You're right. The story doesn't end there. We've got to talk about continents on the move, what we call continental drift.
Continental drift, yeah, I remember hearing about that. But honestly, I'm not sure I ever really got it. Back to basics, what are we talking about here?
It's just what it sounds like. Those continents, they haven't always been where they are now. They've been drifting for millions of years.
Drifting,
Oh.
on their own. What's moving them?
That was the big mystery. Way back, map makers, they noticed how some continents, like South America and Africa, their coastlines almost fit together, like puzzle pieces.
Yeah, I've seen that.
And then, in the early 1900s, a scientist named Alfred Wegener, he came up with this theory, continental drift. He even said all the continents were once one giant landmass. He called it Pangaea.
Pangaea, yeah, rings the bell. But if Wegener had this theory, what was the problem? Why weren't other scientists convinced?
Wegener had the pieces, but he couldn't explain how they moved. He had some ideas, but nobody really bought them. It took more evidence, which came later, after World War II.
Okay, what changed?
Scientists started mapping the ocean floor, really looking at it for the first time. And they found these huge underwater mountain ranges, trenches, even underwater volcanoes.
Okay, now this is starting to sound kind of exciting for geology.
Mm.
Mountains, volcanoes under the sea, what else?
And here's the thing. The ocean floor wasn't what they expected. It wasn't covered in old sediment.
Yeah.
The rocks near those mountain ranges, the mid-ocean ridges, they were young, much younger than the rocks on the continents.
So new ocean floor was forming. How's that even possible?
That's where seafloor spreading comes in. Another scientist, Harry Hess, he figured out that magma from inside the Earth, it rises up at these ridges, creating new crust. As it does that, it pushes the older crust away, like a conveyor belt.
Wow, so it's like a giant underwater factory making new Earth.
Pretty much. And there's proof. They found these patterns in the rocks, magnetic striping it's called.
Magnetic stripe?
It's like the Earth took a snapshot of its magnetic field and locked it into the rocks. This field, it's flipped directions many times, and you can see those flips in the stripes on the ocean floor.
Okay, that's pretty wild. So new crust is being made, the continents are moving, it's all making more sense now. But you mentioned plates before. How do they fit into all of this?
All right, here's the big picture. The Earth's outer layer, the lithosphere, it's not one solid thing. It's broken up into these giant pieces, like puzzle pieces, but massive. We call them tectonic plates. And they're always moving really slowly, just a few centimeters a year.
So the continents, they're hitching a ride on these giant plates, like passengers on a very slow ship.
That's a good way to put it. And just like ships going different places, these plates, they move in different directions. And when they meet, that's where things get really interesting.
Okay, what happens when these plates bump into each other?
Depends on how they meet. You can get mountains, volcanoes, earthquakes. It's all connected.
So it's like a slow motion demolition derby down there.
In a way, imagine two continents colliding head-on. They crumple up. That's how you get huge mountain ranges, like the Himalayas.
No way! The Himalayas are still growing.
They are. And if an ocean plate hits a continent, the ocean plate gets heavier. So it gets pushed down, subducted under the continent.
Mm.
That creates those deep trenches in the ocean, and it can cause volcanoes, too.
So that's how we get mountains and volcanoes. What about the other ways these plates meet?
When they move apart, that's where new crust is formed, at those mid-ocean ridges. And then there's when they slide past each other. That's what causes a lot of earthquakes, like along the San Andreas Fault in California.
That's a fault everyone worries about, right?
That's the one. All that movement, that's what causes those earthquakes.
This is amazing. So these massive plates are moving, creating mountains, volcanoes, earthquakes. It's like a planet-sized ballet, but in slow motion.
That's a great way to describe it.
So where does this all end up? If continents have been moving around for millions of years, could they ever all drift back together? Another Pangea someday?
That's the big question. Scientists believe these cycles, continents coming together, breaking apart, it's happened before. Many times. So who knows what the future holds? It's definitely possible.
This has been incredible. From the Big Bang to giant plates moving under our feet, I never knew Earth was so dynamic.
Me neither. And the best part is, there's still so much we don't know. That's what makes it so exciting. Every answer leads to more questions.
Well, I think my brain needs a break after all that. Thanks for joining me on this journey through billions of years of Earth's history.
It's been my pleasure.
Yeah.
Until next time.